All right, welcome back to Physics 1812. Today this is our last and final class period. After this, go home for Thanksgiving break, and then we'll have our exam 4, the week of final exams. Even though we have a meeting time, we're pretty much asynchronous, so I'll have the exam available over a couple of days. That includes our regular meeting time, which I think is on the 4th. I'm not sure, but I'll get it started a little early, probably at midnight on reading day. See anybody wants to take it early and get it over with. So today's lecture is basically, it won't take too long, I don't think. We'll do some example problems, but we're just going to look over what's going to be on exam 4. And it's not a cumulative. We don't have a cumulative final. So it'll just be on chapters 15, 16, and 17. And you should be able to pull up, I've got some formulas for Unit 4 exam and a couple of graphs. You should be able to pull those up. If not, I'll make sure they're available after class here. And the formulas that I have available to you are just the ones that you used. A lot of them come from chapter 17, the last little push through some of these equations that we went through in numbers 5 and 6. Got those equations, and also several others. The equations for the frequency of a pipe closed at one end, which is one way to model the vocal tract, or of a Helmholtz resonator. Find the frequency of a Helmholtz resonator, which is the second way to model the vocal tract. And so we'll take a look at both of those today. The log equation is in there. The equation for pressure. I've got conversions in there, so you'll be able to convert 1 meter squared to 10,000 centimeters squared, or vice versa. Also, 1 million centimeters squared is 1 meter squared. So I do have some of those conversions for you. And I've got the graph. There's a graph of the formant changes, similar to what we looked at in the last chapter, where we had to take a look at the way first and second formants changed in order to make evaluations of the consonants following vowel sounds. So the one I've got loaded up for you is the vowel following the consonant D. So D, de, da, do. And that graph is there, so we're going to have a question about the formant changes when you say a vowel following the consonant D. And we'll take a look at that in a few minutes. All right, so let me grab my book here. And I'll be looking at both my book and the computer. Since we're talking about it right now, let's just go straight into that certain idea that we were just mentioning there, which I believe was, let me find it here, in chapter 16. Let me take a look. Oh yeah, page 362. So the graph I've got printed out for you is that middle graph, beginning with the vowel sound D. And it's and so look for questions like, when you say a certain, for example, if I were to say the word da, you could take a look there and verify that when I say the word da, the second formant drops after the D sound. The first formant raises after the D sound. And if you needed to, you could probably go in there and by recognizing that frequency changes, you can tell me how much the frequency changes during that D sound as the formant rises. The first formant rises and the second formant drops. So that's an example of some questions I might ask about that graph on page 362. If we were to go back, and let's just start at chapter 15 and take a look there. I've got a question or two about the actual vocal organs. So go back through there. We had a day off where we were to watch some videos, and some of those videos sort of went through the building step by step the vocal apparatus. So be sure you go back through there, know your parts of the vocal organ, and there will be a couple of questions just about the physiology of speech. So watch out for that. Also, the next thing that we kind of got there were speech production, resonances of the vocal tract formants, so classifications of English consonants. And so make sure you go through these two tables on page 344 and 345. In those tables, first of all, you got the pure vowels and then the combined vowels, which are called diphthongs. And then on the next page, 345, we have these different types of articulations for consonants. And so make sure you know the difference between plosives, fricatives, nasal semivowels, and liquids, and examples of each. Also be sure you know the difference between unvoiced and voiced. So unvoiced is when you leave your vocal folds slacked and just air passes through. Voiced is when you tighten the vocal folds and you create the sound of the vibrations of the vocal folds. And so some of that has to do with how consonants, whatever, interact with the physiology of the vocal apparatus. All right, so that's sort of the most important thing there. And I'll also go through, sort of like I've done in the past, and take a look at your exercises and tell you which ones to study a little more carefully. All right, so along with this, one of the first things we got to was looking at models of the vocal tract. And so there are two ways that we model the vocal tract, and either of those can be on the exam, and that was using the model of the voice as a tube closed at one end, like we see on page 347. And the other is the model of a Helmholtz resonator, like we see on page 348. And if you remember, at the back of chapter 16, I'm sorry, to read chapter 15, there were a couple of exercises that sort of dealt with that. And first of all, let's see here, I think it's 5. Yeah, we calculated on number 5 the frequencies of resonance for a tube, 16 centimeters long, closed at one end and up on the other. And I'm gonna of course open up the homework keys. I was waiting for everybody to get those in, so we're going to open up those so you'll be able to study those keys over Thanksgiving and into the exam period. And 5 and 6 are in there, so I'm not going to work these particular problems on the board right now. But be sure that you are able to, given a certain length tube, in this example 16 centimeters, to first of all figure out what the first several resonances are. Okay? And the equation that we use for that, let me just zip back up here. The equation that's given to you, and I'm going to just refresh your memory here. F to the n power, not the n power, but subscript n. In other words, any frequency at harmonic number n, where 1 would be the fundamental, and then stacks above that, is equal to v over 2 pi times, I'm looking up a line here, I'm a long way from my computer, nv divided by 4L. And this is where n is equal to 1, 2, 3, on out to as far as you want to go. So this is the main equation. N is an integer value. You just multiply by 1, 2, or 3. And so basically what we're saying is, if we were finding the fundamental, it's going to be frequency is equal to V over 4L. Why is that? Because when a tube of length L begins to resonate, there's a quarter wavelength set up in that tube. And if a quarter wavelength completely fills the tube, then the total wavelength is equal to 4 times L. So frequency is very simply just velocity over wavelength. This comes from the wave equation, rearranged to solve for frequency. Frequency is equal to velocity over wavelength, where the wavelength set up in a closed tube is equal to 4 times the length of the tube. So that's basically what we're doing there. And then this is the fundamental harmonic. Then everyone above that, we're just multiplying by an integer. So if the fundamental equals 100, then the second is 200. The third is 300. The fourth is 400, etc. I'm sorry. It's every odd. It's every odd. So there's no second, no fourth. You would say the first is 100, then the third would be 300, the fifth would be 500, etc. And so what happens is those even integer harmonics don't exist with a closed at one end tube. They only exist as far as tubes go, in tubes that are open at both ends, or a vibrating string, then you get the even harmonics. But for tubes closed at one end, like the vocal tract, or a bugle, or an oboe, or something like this, then you just get the odd numbered harmonics. So the answer to this one, if it were, the fundamental were 100,